Hi everyone. My name is Kepeng. I'm from Technical University of Denmark, and I'm very happy to be here to present to my recent work under supervision by my supervisor, Professor Jochen Teizer. And this study focuses on automating the process of connecting construction site safety monitoring and construction site safety planning. So I give you a brief introduction about the motivation and the background of this work. So enhancing safety for construction workers usually involves comprehensive tasks, for instance, safety planning and safety monitoring. And there has been abundant research on how to automate the individual tasks. For instance, safety rule-based checking algorithm in 4D beam for safety planning. And also there are a lot of emergence of various sensoring technology for helping safety managers to do the safety monitoring. However, we still identify a research gap. There is a lacking connection between safety planning and monitoring, which often leads to the issue of limited interoperability and undermines the advancement in the automation technology. And therefore, we raised our research question. How can we effectively use the output from safety planning to guide safety monitoring? And how can we reversely enhance safety planning with the results from safety monitoring? And to answer the questions, we proposed a framework. So the framework first utilizes the existing methods. We create safe beam and resource protective envelope following others methods. And then we create a tracking platform where the safe beam and the resource protective envelope are integrated. And then the real-time locations are also collected on the tracking platform. Then we apply safety incident detection algorithm to detect and analyze the incidents. And furthermore, with the analysis result, we update the safety model and the protective envelope of the dynamic hazard resources on the construction site. And this framework was first implemented on a real-world construction site. It's a pilot site for of a staging area for railway renovation project. And first, health safety manager has to designate different zones for machine workers and other resources on the construction site. And then we create this site layout model based on the manager's advice. Then we apply hazard zone detection algorithm, rule-based hazard zone detection algorithm divided by my colleague Carson, who's not here today, by the way, to detect the potential hazard zone in the 4D beam. And here is the example. This is collision zones between workers, worker path, and the machinery movement space. And after the creation of the safe beam, we implemented the framework on the construction site. So over the 2 days, we tracked 4 workers and 1 telehandler. Workers were wearing the safety vest, RTK embedded safety vest. So we chose RTK GNSS at the tracking technology. And 1 RTK sensor was mounted on the telehandler. And alongside the installed RTK sensors, we also placed 1 RTK sensor statically for 3 hours to test the precision. And we can see from the result, 50th percentile of the locations tracked fell within 2 centimeter, which means even subtle movement like wiggling can be detected on the construction site. And from the observation of the construction site, we recognize two kinds of hazard zones on the construction site. First one is semi-static hazard zones, which actually aligns with detection in the 4D beam. It's a hazard zone embedded into the site layout and schedule. And the image shows an example where a pedestrian walk past colliding with the machinery zones. And the other type of hazard zone is a dynamic hazard zone, which is often caused by the operating equipment. And in our case, it's the telehandler moving the gravel back and forth. And the next step is trying to integrate the tracking trajectory with the safe beam. So first, we have to unify the coordinate system. So the tracking system, coordinate system has to be converted to the local coordinate system in the beam model. And then we extract designated zones and semi-static other zones pre-identified in the safe beam. For instance, there are example like this is a semi-static zone because that's an intersection between the walking path and the machine movement space. And then we locate operating equipment based on the track location of the telehandler, and we create dynamic hazard zone around the equipment. So here's an example of the dynamic hazard zone we adopted in this this work. So it's a 2-meter boundary safety envelope surrounding the telehandler. And we detect two kinds of safety incidents, which directly related to the two types of hazard zones. First is pedestrian actually leaves the designated pedestrian walkways, and the other is walker walking too close to the operating machine. And from the results, we can get some very insightful information. So first, from the counts of incidents, we can see Walker 2 has the most incident, which is actually significantly more than other walkers. But looking into the detail of each incident, we can see Walker 3 actually had the longest incident. And we want to further understand why is this case. Then we look into the incident locations. And from the left image, we can clearly see Walker 3 actually significantly violates the safety regulations by walking into the machinery zone. And for Walker 2, who has the most incidents, actually the most common incident types is the deviation from the safety incident, safety path. And from the heat map, it can also be confirmed because walkers deviate from the safety path, especially at the corner. They try to take a shortcut, and that's where the incident occurred the most, and also indicating higher risk of next incident occurrence at that location. And we also have a on-site image to confirm our inference. So this is the corner where workers have to wait and avoid the collision with the operating machine. So that's why they kind of deviate from the safety path at the intersection between machinery space and worker path. And it's also marked on the tracking platform where the high incident occurrence is. And for this type of incidents, we kind of offer the feedback to the safe beam. So we recommend the installation of protective equipment, and we mark or extend the walkways on the ground surface. And we also installed the physical protective equipment like a concrete barrier. And the other level of feedback we provide is related to the human behavior. We did a preliminary behavioral study on the relationship between the safety distance and the incident occurrence. We can see workers spend 50% of the time within 2 meters to the machine, which it's fine in that construction site, but for different construction site, the statistics or the recommendation has to adjust. That's why we, except for providing personalized feedback to construction worker, we also recommend to adjust the size and shape of protective envelopes of the construction machine. And here is an example of a bigger picture. How can the framework be integrated into a digital twin? So digital twin is actually a perfect framework for this small framework. So health and safety manager can view and assess the results, safety results from this user interface. And now I conclude my presentation with the contributions of this work and the future potential. So in this work, we developed a framework to integrate SafeBeam and location tracking technology. And we evaluated the RTK technology. We implemented in a real world construction site for applicability validation, and also we provide some examples of detailed safety monitoring and feedback. So in the future work, we want to understand and learn more about the complex and dynamic construction site operations, which can be different causes lead to the incidents. For instance, if it's related to worker behavior or if it's related to the construction site layout. And yeah, in the end, I also want to acknowledge the support provided by the EU project, Talk, and thank you for the audience.